TU Delft, Max Planck Institute. And without further ado, please give a warm welcome to Doğa.
Is the voice okay with the mic? Yeah. Okay. Cool. Yeah, thanks so much for the introduction, Xiao, and also for the warm welcome. Yeah, really nice to be here today with you all. And yeah, as Xiao said, I'm a PhD candidate with Stephanie Mueller at MIT and also a student researcher at Google Zurich. And today I'll be talking about my research on embedded machine-readable tags for connecting real-world objects to digital worlds. I'd like to start by talking about my motivation first. So let me briefly explain why tags are important for mixed reality and ubiquitous computing. Attached objects for identification, tags are actively used in many industries like shipping, retail, robotics, and manufacturing. And now with augmented reality getting more popular, wearable devices promise to enrich our daily interactions by providing information to us whenever we need it. These devices need to constantly identify what is around us and display related digital content. Just as an example, imagine that you're at a store browsing different items. You want to get further information about a product, like the unit price, calorie information, or cheaper alternatives. For this to work, the objects and products around us need to carry spatial labels that uniquely describe what they are and communicate this information to digital devices. For example, you have probably heard of digital product passports, a very interesting concept that is being proposed by the European Union. And while barcodes like QR codes are great for this purpose, it is not plausible to just slap a QR code on everything around us. You know, they're not typically visually distracting and not as durable or secure as other tags like RFID. I envision that one day, every physical object in our lives will contain an integrated fingerprint that will give us information about the object. And we will be able to access this just by pointing our devices at the objects. This is familiar to us in a digital ecosystem, where audio or image files include metadata embedded in them that helps the user seamlessly identify and get more information about them. I'm planning to transfer this paradigm to physical objects using physical unobtrusive tags. These tags will be an integral component of the object right from the fabrication stage. I work towards this HCI mission using novel techniques in digital fabrication, imaging, and computer vision to create different types of unobtrusive tags. So today on this slide I have natural tags and engineered tags. And I want to talk about a few projects that fall into these categories. So first, let me talk about natural tags. These allow us to leverage objects' natural fingerprints as an ID, such as their micron-scale texture. And as an example, I want to talk about my WIS 2021 project, SensiCut, a material sensing platform for laser cutters using speckle imaging and deep learning. So here's a question for you all. What materials do you see here? For example, can you tell me which one is acrylic? Any guesses? 4, 5? Well, it's tough, right? So because these are actually all totally different things, and acrylic is the first one. So for us, it's hard, but for SensiCut, it can sense and distinguish between these different materials using their natural fingerprints, and then set the correct laser power or speed values for cutting or engraving them, or even warn users if the chosen material is actually hazardous for laser cutting. And to clarify the motivation here, let me start by explaining the common laser cutting workflow today and why this is a good example for using natural fingerprints. So when a user wants to laser cut a design, they first select the material from stockpiles in a shared workshop, like this one in our lab. And you have probably experienced similar things, but these materials are often left unlabeled or maybe difficult to distinguish. So let's say you picked one sheet and then you launched the laser cutter software, and hopefully you made an educated guess and selected the right one from the database. But if it's not the right one, what would happen, right? So it's tough, even if you're not an expert, it's even tougher. And if it goes wrong, well, the best case scenario is you haven't applied enough laser power, so the outline is not cut through yet. So you can put it back in the laser cutter, try to align the sheet at the same position, and apply the laser again. And more concerning is that you chose a material like PVC that is not intended for laser cutting, so it releases toxic fumes in the lab. And perhaps the worst scenario, the laser power is too high, and then suddenly there's a fire in the workshop. So we really need this extra layer of safety mechanism here. Let's look at what solutions have been proposed so far. The first solution that comes to mind is adding a camera to the laser cutter so it can automatically identify the sheets. However, a single camera can be easily fooled by cases like this one, where the sheets have the same color, but require completely different settings. And one solution is to attach sticker tags like QR codes to individual sheets like this one. But the problem is during laser cutting, like you cut off little pieces, right? So if the code is cut off, then you cannot use the rest of the sheet anymore. Or if you put the wrong tag, it's going to assume the wrong type. So in SensiCut, our goal was to identify materials by leveraging their inherent features. And we do this by using an optical method called laser speckle imaging, which helps us sense the surface's microstructure. So this is how it works. There's a laser source, and it interacts with the very tiny features at the bottom, at the surface, on the surface of the object. And when the light source is on, when the laser is on, it emits this beam, and then it interacts with the surface and gets reflected towards the image sensor. And on the image sensor, you get a two-dimensional image shown caused by the mutual interference, either constructive or destructive, and so you get these dark and bright pixels. And here you see this in action. The camera has no lens, so we see nothing in regular lighting, but when I turn it on, you see how this crisp speckle pattern forms. And the distribution in these patterns are distinct for each surface, and therefore it lets us easily classify the material. And to make this more clear, I went into a material science lab and used an electron microscope to get these micron-scale images in the middle. And this machine costs thousands of dollars, whereas the speckle imaging technique that we use only costs $20, $50. And now that we know about this technology, I want to talk about the user interface we built for it and what kind of applications we use it for. So I worked on this project during the pandemic, and everyone was trying to come up with ways to rapidly fabricate face shields and masks. So in this example, my friend Jack wants to quickly fabricate a face shield for himself. And so he downloads an open source file from the internet, and then he goes to the lab, picks some flexible plastic, puts it in the laser cutter, and then he launches the SensiCut software, puts the design file there, and clicks the pinpoint button to make the laser cutter go to a point on the sheet. And once identified, it turns out that it's actually hazardous for laser cutting because SensiCut knows that it's polycarbonate, which is not meant to be laser cut. So then Jack goes back to the materials, picks a different sheet, and repeats the process with SensiCut. So this time, turns out the material is acetate, which is safe. And so Jack just confirms this, and then enters the thickness value of the sheet. Today you have to do this manually still, and then clicks continue. And once confirmed, the system automatically retrieves the appropriate settings and starts cutting the sheet. And he repeats this procedure for the second part, the visor. And this time the sensed material is acrylic, and the system automatically cuts the shapes with the right settings for it. And now that all parts are here, Jack can assemble the face shield. Ta-da! I also want to show you another application, very common among laser cutter users. Many of us often engrave custom designs to personalize things such as text or patterns. And with SensiCut, we can take this one step further and engrave objects that consist of different materials across its surface. So right now, this projector doesn't really show it well, but you see how this floral pattern was engraved on an object that consists of wood and rubber at the same time. And for the sake of time, I'll skip how it works, but perhaps that gives you an idea. And we use machine learning to do this classification. So this is how it works under the hood. And we captured the data set, obviously. For that, we wrote a script to automate the laser cutter's movement and image capture. So this is how it looked. So everything's automated. And in total, we captured more than 38,000 images. And we evaluated the accuracy across 30 materials. And on average, the accuracy was higher than 98%, which is enough for our purposes. And so that was SensiCut as an example of natural tags. And if you're interested in the technical details, we can talk more. And next, I want to talk about the second category, engineered tags. So here, I mean that we can engineer the type of information or pattern we want to embed on an object during the fabrication process. And yeah, in the email that was sent out, maybe I used a different classification, how I'm pitching the different types of tags, but it's still something that I'm framing for my thesis. So that's why there might be a reason. But now I want to talk about my Chi 2020 project called GID. And there we presented an approach for identifying 3D printed objects using what's called slicing parameters. And our motivation was to integrate tags into three-dimensional objects, like I said. And there has been some previous work in this area. And some approaches included, for example, carving QR codes onto the object surface, or sort of projecting a linear barcode on the outside, or even creating a more customized or natural-looking pattern. But as you see, all of these tags are visible and they dramatically impact the look of the object. So researchers then came up with new techniques to hide these tags. For example, AirCode from WIS 2017 uses a camera and projector setup to detect gaps beneath the object surface. InfraredTags uses a terahertz scanner to detect similar hole-based tags. And LayerCode uses a modified SLA printer and customized resins to create hidden barcodes. But as you see, these methods require either the use of specialized or high-cost equipment. So with GID, we just wanted to have something that is unobtrusive, but also easy to fabricate and that can be detected using low-cost scanning or scanning tools or cameras. And then we said, okay, like how about we actually don't create these things and just utilize what's already there. So GID actually uses the patterns created by the regular 3D printing process. So as you see, when you 3D print an object, you might have noticed it has inherently distinct features due to the path the printer lays down. And if we have multiple copies that each have a different path layout, as you see here, then we can actually tell them apart. And so let me how we use this feature in our system. So I want to give this application example where we want to create a set of 40 unique key covers for our lab so that we can give every student a key. But also at the end of the semester, we want them to return the keys and we want to check off who has returned their keys. And using GID, we can quickly do that. So how does this work? First step is the tagging. We have this user interface where you can load a 3D model, and then you select how many copies you want to have. And then it slices each instance with a unique set of slicing settings and shows the results. Here you see the differences in slicing settings, for example, in the line angles. And now we can enter a label in the form of a text or image, but in this case, we enter every student's name. And finally, we have the different G-code files that we can send to the 3D printer. And so we get our objects in the end. So the second step is identification. For this, we have an application for Android. And you first select the model you want to scan, and then the app sort of helps you align the camera image with the object by showing a target outline and a detected outline, similar to like how document scanning apps work. And when the outlines are aligned in the setting, it automatically captures the image and processes it, and then it retrieves the user assigned label, and then you get what you want in the end. So in the previous scenario, we talked about surface textures, but also 3D printed objects have unique interior structures, and GID could also sense that using a light source. And this is just an illustration. So if you shine light through 3D printed objects, if the light is strong enough, you can actually see the infill patterns, and you can tell them apart. So you have grid, triangular, trihexagon. Yeah, so, and what is this useful for? So two kinds of applications I want to talk about today. One of them is user identification. In this example, we have 3D printed mugs that each have a different infill, and with this coffee maker, it can detect that using a camera and a light source. And after recognizing the mug and identifying its owner, the machine can pour your favorite drink. So this application is for makers specifically, so it's kind of more niche, and for the sake of time, I'm going to skip it, but you can look at it on our website. So that was GID, which is great for distinguishing between different copies of objects. However, one limitation is that like you cannot put like a custom a string, a custom URL. So how can we actually like embed data into the object? That was something that we wanted to explore, and I want to talk about our KITE 2022 project, infrared tags. Now, and infrared tags are invisible markers embedded into objects that are 3D printed with an infrared transmitting material. And even though you cannot see these tags with the naked eye, they can be captured using an infrared camera and image processing and computer vision techniques. And in this project, our goal was to create invisible tags that carry information that can be fabricated on common printers and, again, detected rapidly using low-cost sensors. And we achieved this by using an affordable region of the electromagnetic spectrum. And by that, I mean the near-infrared spectrum. And let me explain what I'm trying to say. So this is the electromagnetic spectrum, as you might remember from your physics class. And here's a section of it. And on the left side, we have the visible region, and on the right, we have different regions within infrared light. And because infrared cannot be directly seen by humans, we can use these regions to encode and decode invisible information. Here you see some of the regions within infrared, from near infrared to terahertz. And if you want to image objects in long wavelength infrared or terahertz, so these guys, then that's going to be expensive because the longer the wavelength, typically the higher is the price tag. However, near-infrared cameras are much more affordable. So in our project, we just use a $20 camera by Raspberry Pi for our purposes. So now that we know more about near-infrared, I want to talk about the fabrication process. The one key observation here is that many plastic materials actually pass near-infrared light, and you can see them in TV remotes, for example. And for our goal, we had to find a similar material, but for 3D printing, right? And after extensive testing, we decided to use this filament manufactured by 3DK Berlin, and it's actually based on PLA, so it's the most common printing material, and it's which it means that it's cheap, and also you can just use it at regular temperatures. And so we tested how this compares to regular PLA filaments and measured the transmission characteristics using a spectrophotometer. And I'm not going to go into the details today, but basically we combined these two spools of filaments using dual nozzle printing to make use of this transmission difference. So let's talk about the applications. Infrared tags can be used to embed data about the object into the object itself. And in this example, we have embedded the mug's fabrication link So if you like the look of an object, you can take a picture of it and download a copy of the 3D model and maybe print it at home. So how did we put this URL as a QR code? Well, you can actually developed an interface for a plugin for Grasshopper, Rhino, and you can actually then just send it to the 3D printer, and you see the print halfway through. On the left, the visible view, and on the right, the infrared view. And to detect the tag, users can attach our imaging module to their smartphones. And this consists of low-cost components, as shown here. And well, the nice thing is that it's actually not necessary to use this if your phone already has an infrared camera. So there are some phones on the market that come with a near-infrared camera, such as OnePlus 8 Pro. So it makes a cool demo. And the second application I want to talk about today is about augmented reality interactions. So in AR view, it can show you, for example, the control menu of a device or an IoT object. And you can adjust this volume of a speaker. And oh, this is a bit different. So this is about actually more spatially aware augmented reality, I would say. So in this example, the visible surfaces of this Wi-Fi router only have its network name embedded, whereas for safety reasons, the passcode is only embedded on the bottom of the router. So you have to flip it to connect to it automatically. And the final use case is you see how this plastic disc, which doesn't have any electronics in it, can be used as a game controller. But as you see, it's not super robust. So that's why I'm going to talk about what we did about that. But that was infrared tags as an example of engineered tags. So if you're interested, you can check it out on GitHub. We open sourced it a while ago. And now I want to talk about, so like infrared tags was pretty cool, and we got some questions, inquiries about it, and we started thinking about a couple of follow-up questions, including how to make them more robust, more inherent to the fabrication process, and how can we increase the data capacity. So I want to talk about these different things quickly. So the first one was, again, how to increase the robustness, the contrast of the markers to achieve real-time tracking. So we just presented this at WIS 2023, BrightMarkers, that tried to answer this question. And here we used a fluorescent material. So you see on the left the visible view and on the right the infrared view. And that really shows, that really makes the markers more crisp and a high contrast. And how does this work? So we make use of the physical phenomenon, optical phenomenon, fluorescence. And here our markers made from an infrared fluorescent filament shifts the wavelength of the incident light. So our optical detection setup can just filter out all the noise to only have the markers present in the infrared image. And this is what the special infrared fluorescent filament looks like, and it's made with ABS. So you can just use it at typical ABS printing temperatures. And I want to explain briefly how this works. As I said, fluorescent material emits infrared at a higher wavelength than the incident light, and we can use this characteristic to separate the marker from the rest of the image. And here the yellow part represents the marker embedded in the object. And normally, well, you see this in this illustration, the emitted fluorescence is not visible in the image, and because it gets washed out by other lights in the scene. As you see in the end, in the camera, you don't really see the marker. But if you use a specific optical filter, like this one, then that blocks these two guys over here. So you only get the fluorescence into the camera, and then you can actually image the marker and just the marker. And this is how it works in practice with our hardware. So yeah, and you just see the marker glowing sort of invisibly. And using dual nozzle 3D printing, you can combine this with other types of filaments and other types of colors, and which is also another benefit over our previous work in infrared tags. And we designed imaging modules that make use of this property that you can attach to your phone or attach to your headsets. And here are some applications. So this is for mixed reality. You can track object parts precisely, and then you can sort of, even like this speaker is not plugged in, so it's not powered on, but you can still track its knobs to turn it into a tangible interface. Or you can create haptic props by using passive electronics-less objects. And the second question we asked ourselves was, so moving out, how can we use the inherent fabrication associated artifacts to store data? And this is from SCF 2023, a new paper called Struct Codes. It's similar to the GID work that I mentioned, but more focused on laser cutting and data storage. And the applications are, again, more centered around augmented reality, how to augment objects with relevant and contextual information well, how does it work? Then I can switch to the next slide. So it embeds unobtrusive codes by slightly adjusting laser cut structures, such as finger joints and living hinges. So by slightly modifying the visual artifacts, you can actually represent bits, zeros and ones in the object. This last one, we asked ourselves, okay, like there's only so much data that we can encode into these objects, like maybe a short string, a few characters, but how can we increase that so that we can maybe achieve network-free interactions so that you don't have to connect to the internet to view something. And this was the result of my Adobe internship project called Standalone stands for Standalone AR Documents. And here we, again, make use of near-infrared technology, but more for documents, paper documents. So we use a special ink that is only visible under infrared, near-infrared. And then that way we can print this huge QR code that is as big as the paper sheet into the paper, and then all the information that's encoded there, we use it to create stuff on the go in augmented reality. And you can imagine this can allow for a variety of different interactions with paper media, such as for education or even for packaging and things like that. But yeah, so to conclude, as I explained in the beginning, my bigger vision is to enable users to seamlessly identify and interact with objects, products, and materials in their surroundings so that they can access information related to them quickly and seamlessly. And I guess, yeah, so as a side note or reflection with all of these different projects, it makes more sense to classify them as natural tags, interior tags and structural tags. So I think that this is how I'm going to actually reframe some of the things later for this talk. So just as just like reflection for myself. But I'm also curious to hear your thoughts, what you think about all of these different directions. And in the future, there are some aspects that I want to explore. For example, like I said, digital product passports, something that's important to the European Union to improve the sustainability, the transparency, and the availability of product information. And this can help us with a bunch of different things, both from the side of manufacturers and consumers, and also to enable more personalization using new form factors that are coming out with Apple Vision Pro or different headsets that are going to be released by different companies soon. And you can imagine that in the future we could just like go to the grocery store and our smart glasses can tell us what's the best product or what kinds of things we can be interested in or what discounts we can get and things like that. And another possible area that I'm interested in is accessibility, specifically for users with visual impairments. So you can imagine how embedded tags could help a blind user sort of say, okay, like something is not microwave safe, or perhaps embedding accessibility captions into documents that often get lost when a document is printed. So yeah, these are just some things that I'm thinking and tinkering about. And lastly, I want to thank my mentors and collaborators at different places who have helped me so far. So thank you, and also thank you so much for your time, and I'm happy to answer your questions.
Hey, Nanu, what? So if you have any questions, please raise your hand. And don't forget to speak in the microphone while asking your questions.
Some of your examples were about using, for example, mugs or stuff that we use for food consumption. But as you probably know, like some materials or fabrication processes are not compatible really with that kind of applications. If we wanted to make them food safe or food grade, we should do some post-treatment, or aren't you afraid that the post-treatment could, I don't know, obscuricize the tag behind or something like that?
Yeah, that's a great question. Yeah, that's something that I thought about too. Well, for PLA, for example, for PLA plastic, they say that. I mean, it's often labeled as biocompatible. So, but I mean, I haven't tried myself to drink out of a PLA mug, so because these are obviously research prototypes. So in the future, perhaps it would be interesting to explore the biocompatible tags, if that's something that we could. I know there's a lot of biocompatible research that's being conducted here, so I think there's definitely some value there, potential there to explore. Yeah.
I have a question for the natural tag. Did you have some difficult, for example, if you buy MDF and you have
So it's a little hard to hear.
Excuse me. Yeah, it's better. Okay. For the natural tag, I have a question. Did you have difficult when you, for example, painting on the MDF and you still recognize it?
Yeah. Yeah, so that's a great point. So basically, for natural tags, in the example of SensiCut, you have these natural objects, right, or natural laser cut sheets like MDF, like you said, medium density fiberboard, or acrylic, which is sort of like a synthetic material. So what would happen if you post-process them, or if you paint on them, right? So well, there we make use of the natural fingerprint of the object, the natural microsurface. So if you actually destroy the surface properties, then you would not be able to identify the material anymore, because unlike, for example, your finger, like if you maybe like scratch your own finger because you're a living creature, it would regrow the fingerprint, but because these materials don't have the capability to regrow their IDs, that wouldn't be possible. But I think, for example, like perhaps spraying, like as a post-processing, like maybe you have some sort of wood and you want to spray it with a color, with a paint, then that could potentially preserve the natural tag, because usually that's like more homogeneous surface finish. So it's all about if the defect you're causing is sort of destroying the whole structure, or just adding sort of like a DC, like a superposition sort of, if it's just like adding one extra layer of thin paint or something. Yeah. So it depends what kind of post-processing you want to do, I would say. And in the worst case, you can just retrain the machine learning to suit your needs. Yeah.
Hi. Hi. Thank you. I had a question about the fabrication process of the 3D printed infrared QR code hiding. How do you distinguish which part of the filament is the QR code or not? I didn't understood that.
So which part of the filament is?
So 3D printed is layer by layer.
Yeah.
But I guess that as you want two different property to light, one that doesn't pass light like the QR code part, and another one that transmitted to have the contrast of the QR code. Do you have like two different material in your filament, like double extrusion process?
Yeah, so basically we used dual nozzle printing. So like we used an Ultimaker 3, for example. An Ultimaker 3 has two extruders. So on the one extruder we have the special infrared translucent material, and on the other side we have a different type of material. And then we actually combine them together. Our plugin, the plugin that we designed for Grasshopper, that sort of gives you two files, two STL files, and then you load them together into the slicer, into Cura, and then Cura actually can combine and merge those two STLs so that the printer knows when to switch between those two extruders automatically.
So
that means that for each type of filament you want to print it, each color, you have the equivalent color of the
filament.
Yeah, so you have to decide what color the outside should have. So in the case of BrightMarkers, like for example, we can go back. So like here, right? Like so you would, for this project, you would pick what the object should look like. Like if you want to have a red object, then you would put the red ABS on one extruder, and you would put the infrared fluorescent filament on the other extruder. Yeah. Does that make sense?
Yeah.
Cool.
Thank you very much.
Yes. So I had a question about the SensiCut. So I was wondering, since you showed that it could recognize like acrylic objects, does it also work with transparent objects, like completely transparent acrylics, or even with different opacity? Does it see the same material?
Yeah, that's a great question. Transparent materials reflect less. So the speckle pattern that you get is going to have lower contrast. And also like the machine learning results showed us that the accuracy is lower for that reason for transparent objects. So you can overcome that by potentially increasing the data set size, which we haven't tried, and then retraining. But yeah, definitely, I would say that for this specific implementation, opaque objects are more useful. Yes.
Thank you.
Yeah, great question.
What do you think is the added value of your project compared to traditional methods who, I don't know, to say, you can put this mug in a microwave or just put a drawing in at the not the top, at the bottom of the mug, for example?
Yeah, that's a good point. Are you referring to like the accessibility part, or like sort of something like this, you mean, or?
I mean, it's like a lot of technologies to say you cannot put the spray.
Yeah.
You can just I don't want to criticize your project. It's just a question to understand what the goal of this kind of technology.
Yeah.
Because today, I don't know, maybe we have mug with a little standardized icon to say, oh, you can put this mug in microwave or something. Or yes.
Yeah, that's a good point. So, what's the added benefit over existing tags, right? So, often tags, oftentimes the types of tags that we have are not that durable actually. So even for mugs, these tags actually often get like sort of erased over time, or like for clothing, for example, you have tags over here, right? And often they're too big, and then we just cut them off because they're annoying, right? And then we forget, oh, like, was this washable, or like, how do I fix this or something? So that's actually really bad from a sustainability point of view, and that's why, for example, the European Union is looking into how we can make these tags more embedded into objects, so they become an integral part of the object, and then we can actually keep that information available at all times, and even like till the point of recycling. When things arrive at recycling facilities, oftentimes people and machines have a hard time distinguishing what kind of material is this, how do I recycle it, or for example, I don't know if you know, but like black plastics are often cannot be recycled because cameras don't see them. So like at the recycling facilities, the cameras cannot tell them apart. So I think for these reasons, we need better tagging methods that are both more durable and more robust. Yeah.
I have a question about the 3D printed tags, but not the infrared, the GID, because I feel like there are a little possibilities of printing, like you can go with I don't know, 1,000 units that you can distinguish. I feel you can just go maybe around 360, 140 degrees and maybe a bit more, but how many units have you been able to build?
Yes. Yeah, that's a great question. I didn't talk about that for the sake of time, but let me quickly find those slides and show them. So let's see, let me make these available. But yeah, so that's a great question. And we tried to understand how many instances can we distinguish between. And we did some tests. Basically, we found out at the end that you can have 204 instances just by having a camera, and more than 17,000 instances by using a camera and a light source. And there's some calculation here, like how we came to it, but we just like asked two questions, like which printing parameters can we manipulate at all, and then per parameter, how many variations can we actually detect with a phone camera. So the higher resolution your camera is, the more instances you can actually identify, but we used a more lower end phone just to be more conservative, and obviously you have like all of these different things that you can change, and like this is just an overview of the different things that you could vary. Yeah.
And the same, as an add-on to this question, can't you just like personalize the drawing infill for the surface?
Sorry, could you
like,
hold it closer?
Yeah, sorry. Can't you just, for the infill of the first layer on 3D printed, can't you just do like custom pattern instead of straight lines to have much more possibilities?
Yeah, definitely. So you could actually make even more customized patterns, right? And that would extend your design space. And that's definitely a possibility. And there's a follow-up paper on this called an ISO tag from Kai 2023. If you want to check it out, not from our group, but someone else worked more on this, and it's pretty cool. And they show basically how they can add a bunch of little tiles of different patterns on a single surface to increase the data capacity. So it's definitely possible. Yeah.
Okay,
lots of good
Doga will stick around
questions.
for a bit after
Yeah.
the talk. If not, thank you again very
Yeah.
much.
Thank you. Yeah. Lots of good questions. Thanks so much.
Okay, just before we finish, we have one last question from the online audience.
Oh, okay. Okay.
Someone is asking, related to natural tags, the object change over time, like erosion of a surface,
Yeah.
or is under heavy use, and how reliable could these tags become?
Okay. Okay. Yeah. So it's again about the post-processing question related to SensiCut, and well, I guess there are two things, and I want to reiterate the fact that you can retrain your machine learning classifier to make it more robust to certain conditions. So you could perhaps, like if you want to make it more robust to sanding down the wooden surfaces, then you could do that and capture, I don't know, 10, 20 different sanded down samples and retrain your algorithm. And like from my gut feeling, I would say that you would get as high accuracy. And to preserve the different structures, I mean, I think maybe figuring out like a very thin, even coating might actually be useful to perhaps like to preserve that unique surface microstructure. I think that might be a way to explore, but I haven't tried that yet. Yeah.
Thank you very much.
Thanks.
Thank you.
Okay, may I take a photo, everyone? Okay. It's big, so. Okay. All right, thank you.